What are crystals? How do they work? And why are they so special? Keep watching to find out. So, what is a crystal? Well, we know one when we see one, don't we? They're usually clear, sometimes have nice colours, usually sparkly. But why? Why are they like that when things like wood, for example, aren't? Well, it's how they're arranged at the particle level, down at the level of atoms or molecules or ions. And if you don't know what the difference is between those things, why not check out my other video on the difference between atoms and molecules. But when we get down and look right at that tiniest particle level, we find that they are all arranged in a three-dimensional pattern that we call a lattice. And it can go on almost forever. On the scale of atoms, you can have a wazillion, bajillion, gazillion atoms going that way, another wazillion, bazillion, kajillion that way, another wazillion, bazillion that way. So in fact, we don't need the whole crystal to understand it. We can just focus down on a tiny, tiny fragment of that crystal. And in fact, we don't even need a real fragment of that crystal at all. In fact, what we do is we look at something called the unit cell. Now, the unit cell is not real. It's a little three-dimensional chunk that we could imagine taking out of the crystal. And if we look at just the unit cell, we can understand the whole pattern, that whole three-dimensional lattice. It works in the same way, for example, as a pattern on a piece of wallpaper. You don't need to look at the whole wall of wallpaper to know what the pattern is going to be. So it's that regular three-dimensional arrangement that makes a crystal a crystal. Whereas wood, especially organic matter, doesn't have that arrangement. Now, how and why crystals form depends on what kind of crystals we're looking at. Metals, for example, form crystals very easily because we can think of their atoms as being simple spheres. And there's only certain ways that you can pack spheres together. As we cool the metal down, perhaps from a liquid, those spheres will find a certain way of packing together. And as they lose their energy as they cool down, there will be a certain way which is easiest for them to pack together. If we then start placing the metal under some kind of pressure, there might be a different arrangement which is easier for them. So in fact, the crystal structure of a metal can depend very much on how the metal was cooled and also what kind of pressure the metal is under. And this is a big topic for metallurgists, for example, as they are trying to formulate or produce certain metals, certain alloys that have the exact properties that they want. And molecular crystals form because the molecules have got tiny little electric charges all around their surfaces. And they will maybe find a way that they can match up those charges, a little bit like magnets. And that will help the molecules fit together and slot together in this three-dimensional lattice. But crucially for molecules, they have a definite shape, they have their definite positive and negative charges, so it is maybe a little bit harder for them to form their crystal lattice. Ions form crystals because they have a very strong attraction between different electrical charges. And how those ions fit together will depend on the strength of those electrical charges and also how big the ions are and also what shape they are. A key point is that the particles must be free to move around and meet each other and contact each other and then find that perfect way to slot into the crystal shape. Now, that's much easier if the crystal has started growing already. But if there is no crystal yet, it's very difficult. For example, for salt particles in water, the sodium ions and the chloride ions might meet each other and stick together for a bit, but then the water molecules around them will just come in and break them up again. So crystals need a place, almost a safe place to get started. We call this a nucleation site. Often it's a piece of dust or a scratch, somewhere that those particles can be safe from the rest of the solvent or the rest of the atmosphere, and they can find a little place where they can fit themselves together and then just get that initial crystal started. And once it's started, then there is a surface where more particles can join and the crystal can grow and grow, and then the surface increases in size. A third way to form crystals is by forming a solid directly from a vapor. We know this situation most commonly, of course, from snow or frost, which is where water vapor touches a cold surface and then freezes and makes those beautiful snowflake crystals and ice patterns that we see in the winter. In those cases, the vapor comes out from the atmosphere, touches the ice crystal, and then will rearrange itself so that it can fit into that ice crystal. Now, vapors also need a nucleation site. This is usually a piece of dust, maybe a tiny airborne crystal, and the vapor molecules can stick to that while they wait for other molecules to join them. Without that nucleation site, they are simply likely to break up before enough other molecules can join them to make the crystal stable. But the kind of crystal formation that I want to focus on today is when crystals form from a solution. In other words, we've got some kind of material that is separated into its separate particles. It might be ions, might be molecules, and they are floating around in a solution, within a solvent. If we have a lot of solvent, those particles will just keep floating around. But if we reduce the amount of solvent, for example by evaporation, those particles are going to start bumping into each other, coming into contact much more often. And then they will have to make a choice. Whether or not these particles depends on three sets of interactions. There are the interactions directly between the particles themselves. They might be quite strong, for example, with like ions, or they might be a little bit weak, for example, like molecules. Then there's the interactions between the solvents and the particles. The solvents pulling those particles away from the crystal. And then there's the interactions between the solvent molecules themselves. Do the solvents want alien particles in their liquid? So we have these three sets of interactions, all competing with each other. When we have lots of solvent, it's more likely that the solvent will pull the particles back into the solution. And when we only have a little solvent, it's more likely that the particles will stick together and they'll be able to move around each other until they can find that perfect crystal structure. Oh, and before I forget, if you're finding this video interesting, why not click the like button and help out the channel? Thank you. Another way to grow crystals is to have our solute particles in solution and steadily lower the temperature. Because as we lower the temperature, the particles have less kinetic energy, and that means that once they touch and stick together, it's much harder for them to get away again. That will give them a better chance to stick and form a crystal. Now, one point which is crucial for forming a crystal in a solution is to reach the point of saturation. This is the point where the particles meeting each other now are forced to make a crystal. And that's happening because there is perhaps so little solvent now, or maybe it's happening because the solution has got so cold. Now, growing small crystals is easy. You might heat up some solvent and you can dissolve lots of solute in hot solvent. and then just stick it in an ice bath, cool it down quickly, and you'll get lots of tiny crystals coming out. In fact, that's a technique that we often use in chemistry to purify our chemicals. But for this video, we want big crystals. And big crystals are much harder to make because you have to grow them very slowly. You have to make sure that those solute particles know that it's this one single crystal we want you to join. We don't want you to go off making a new one of your own. Because if the conditions are easy for crystals to form, then many other crystals will form at the same time. And that will mean we can only have lots of small crystals. Or maybe those small crystals will grow into each other and they might not look quite so much as what we think of as a nice clear crystal. So we've thought we'd demonstrate 3 ways to produce crystals and have a look at the results. Now, the first thing we did was choose our solute solvent system. And that's because we wanted a solute which would dissolve into our solvent, but not dissolve too easily. And for that reason, we chose sulfates. In particular, we started with aluminium sulfate. We also chose chromium sulfate, which we'll talk about a bit later. And finally, copper sulfate. Now, those materials are great because we can dissolve them into our water. They will dissolve, but they will also come out of solution quite easily later when we want them to. So we expected our aluminium sulfate crystals to make nice, large, colorless crystals. To our second recipe, we added some chromium sulfate, and that's because in the crystal structure the chromium ion can fit right in there and take the place of an aluminium ion, and it has a lovely purple color, so we can get our color going right through the crystal. There are many places where they'll tell you you can add food dye for growing crystals, which is true, but the food dye is not part of the crystal. It's actually on the outside, or sometimes included on the inside where there's a crystal defect. But with the chromium ions, they are fully incorporated within the crystal itself. So we decided to grow these crystals by evaporation, and that's quite an easy way to grow large crystals in water because water evaporates quite slowly. So with these sulfates, very simply what we could do was to dissolve them at a high temperature. We chose 70 degrees centigrade, and the reason for that was 70 degrees is about as hot as you can go without being dangerous if you spill the solution. It's the kind of ouch, 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 ouch temperature. We added lots of sulfates so that the solutions would be near saturation. Let the solutions cool down, and then we let the water evaporate from the solutions. We did a quick test run using some Petri dishes. And we used the Petri dishes because they have quite a large surface area, and we thought we could evaporate the water fairly quickly. Actually, it took much longer than we were expecting. And that's because at high concentrations, the aluminium sulfate actually forms a gel, which really slows down the rate of evaporation. But we did get our crystals in the end. Here you can see the aluminium sulfate crystals. They are colorless. Now, in chemistry, we don't say white because white isn't a color. White is just the light bouncing off the surface of those crystals. But you can see that because they are on a two-dimensional surface, we get these kind of almost like a slice through the crystals there. And you can see these triangles and these tracks. And these are all based on how those ions fit together into that crystal lattice. But now, because the water has evaporated right down to the bottom of the Petri dish, they can only spread out along 2 dimensions. And then over here, we have a very interesting situation where we have the aluminium chromium mix forming these lovely purple triangles, but with the green solution around the outside. So I think what's happening here is actually very interesting. To understand it, we need to realize that the chromium ions are actually surrounded by 6 water molecules, which are plugged directly into that central chromium ion. They make a kind of molecule called a complex. Now, only that complex can fit into the crystal. On the outside of the crystal, the water is evaporating, it's in very short supply, and those water molecules plugged into the chromium ions are also coming away and evaporating too, leaving behind chromium ions that are very depleted in water now. Perhaps also the solution is getting quite basic and leaving behind hydroxide ions, and chromium hydroxide certainly has a green color. So I think what we're getting is our fully hydrated chromium ions joining the crystal, giving it that purple color, and leaving behind dehydrated chromium ions, which instead of being purple are green. Now, something we learnt from the Petri dish experiment was that the crystals would take a long time to grow if we left them just to form by evaporation. So for the larger experiments, we were sure to add some seed crystals. Now, seed crystals are important if you want to get crystals quickly, because they give the solute in the solution a place to join in and get that crystal going. And now we can see the classic gem style 3-dimensional shapes of these crystals. And the copper sulfate solution also made some lovely crystals, as you can see here. If we look at this example, we can see that beautiful prism shape here, but it's curved. Now that is not part of the crystal structure. That's because the crystal got started on the curved base of that flask. Now, we also tried experiments for growing larger crystals. So we took some small crystals from our Petri dishes and we tied them onto a piece of string, and then we dipped that string into a saturated solution. So the first thing to notice is that that whole piece of string acted as nucleation sites. So we have little crystals growing all the way down the string. But what we can see is here we have successfully grown some large crystals. But they don't look like the large crystals that we know from crystal shops, because many crystals have started growing at the same time and they've ended up growing on top of each other and growing into each other and making these boundary layers between them. Now those boundary layers reflect light, and that means that we can't see clearly all the way through the crystal and it looks kind of fragmented on the inside. But it was after this experiment that we got a very pleasant surprise. We decided to try and grow these crystals even larger if we could. So we made some stock solutions of saturated sulfates, of just the aluminium sulfate and then the aluminium chromium mix. But this time we heated them up and we added extra material. We added some extra sulfates in there and put a cap on the tubes and let them cool down. And within a few hours, we had small crystals, small single crystals at the bottom of the tube. And within a day, we had these large crystals. I was really surprised by this. I did not expect to be able to grow single large crystals this way. I thought the water would cool down, of course, cool down within maybe an hour or so. And I thought that would be too fast to get decent large crystals. I expected lots of small ones perhaps, but not a single large crystal. And the reason for this is similar to the reason we needed to add the seed crystals to our flasks before. It's because this is laboratory glassware and those sample tubes are very clean and very smooth. It was very difficult for those crystals to get started, but one tiny crystal managed to find maybe a little bit of dust, maybe a tiny microscopic scratch on the glass, and that crystal got started. And because the rest of the solute couldn't find a safe place of their own to get started, they all joined that single crystal. So this ended up being a very simple and very quick way of producing a large crystal. Now, you can see some defects on the inside of this crystal, and those defects come because the crystal was growing so fast. So if I really wanted a gem quality crystal here, I would have to lower that temperature very slowly using a programmable oven. And finally, there's one other experiment that I want to share with you. In this case, I wanted to demonstrate a way that we often use in chemistry for growing chemicals of organic compounds. And we often want to grow crystals of organic compounds because it helps us learn things about their molecular structure, maybe helps us prove that we've made what we've said we've made. But it's very difficult. Often we can't use the evaporation technique that we use with the water because they only dissolve in organic solvents which evaporate very quickly. Think about petrol, for example. So we have to find another way to slowly grow these crystals. And one technique is called dilution by evaporation. So what we've got here is a water solution of sugar, an aqueous solution of sucrose. Now we all know that sugar dissolves into water very easily, but it doesn't dissolve into ethanol. So we've got the sugar in a small sample tube in the water solution, and then we've got lots of ethanol in the larger tube around the outside, and the tube has a cap on it. What that means is the ethanol and water can't evaporate into the air, but the ethanol will evaporate into the water that's in the smaller tube on the inside. And that means that slowly that solution will increase its percentage of ethanol until the point where the solution is saturated. Because although sugar is soluble in just water, as the amount of ethanol increases, now sugar doesn't want to spend so much time in the solvent. It's going to start sticking to itself and growing those crystals. We left it to evaporate for about 2 days, but then we decided on a faster diffusion method. I knocked it over. I knocked the sample tube over. And I thought that was that. But so I put the sample tube back up again on the desk, came in next day, beautiful crystals of sugar along the inside of that sample tube. And once again, we had those beautiful crystals because even though the ethanol had mixed with the water very quickly, the smooth glass walls of that sample tube made it difficult for the crystals to form. So as soon as one crystal started forming, and it probably occurred here because of this tiny piece of dust, well, the rest of the sugar had to join in with that crystal. But in real life, of course, you get into a lot of trouble if you knock your sample tube over. Okay, so how about if you want to grow some crystals? What's the best way to do it? Well, it's actually very simple. You can buy lots of crystal growing kits from shops or online, and they're actually very easy to grow. The tricky thing, though, is that you need some patience. So if you have that patience, go along, get a crystal growing kit and have some fun. Now, if you can't afford a growing kit, you can't find one online, or you just don't want the hassle, you can just grow some crystals using simple table salt. Make up a strong solution, dissolve as much table salt as you can in some water. If you find it's still got little bits of grit in it, then you might want to filter it through a coffee filter paper. Leave that solution somewhere to dry out, and it'll make lovely, large salt crystals for you. So how about you? Have you ever used a crystal growing kit before? Have you got a recipe for growing crystals at home? Have you had any lucky accidents with growing crystals, or maybe a disaster when growing crystals? Let us know down there in the comments. So, what makes crystals so special? Well, they certainly look pretty. They have lovely straight edges, and they are transparent, and they have those lovely flat faces that shine light. But that's it. They don't have any special energy. In fact, the whole point of a crystal is that those particles have lost their energy. They're in a very low energy state. Chemically, they're incredibly boring. They are just the same pattern repeated again and again and again and again, a million wazillion gajillion times in all directions. And in fact, even gemstones, those crystals that we'll pay an absolute fortune for, are really not very special at all. Diamonds are actually quite common. Sapphires and rubies and emeralds are literally aluminium oxide with little bits of chromium in them, just like the crystals we grew. In fact, the only thing special about the crystals that we see in shops is that they are relatively rare. And that's because it's difficult to grow them to that size. But actually, there are important crystals in our life. They just don't look pretty. For example, engineers spend a lot of time on growing crystals of semiconductors. By growing these perfect and complex crystals, we can get all of the incredible technologies that we have these days. Other engineers look at developing the crystals of metal alloys. They focus on the very atomic structure of these alloys at their crystal structure to try and give them the exact set of properties that they want for their application. And finally, it's the crystal structure of high temperature superconductors that means they can conduct electricity with zero resistance. Now, at the moment, we need liquid nitrogen to make those materials be superconductive. But even now, materials scientists are working on that, trying to push that temperature up and up and up. And it's going to be the crystal structure that determines if we can ever get room temperature superconductivity. And if we can do that, we'll be able to make inventions that we can't even imagine now. So, well, mostly crystals aren't special, but they are pretty, and some of them might change the world. See you next time.